In our next example, we're going to maximize this profit function, subject to the following inequalities. There are 5 inequalities, but as we frequently have, the bottom two, x and y both greater than or equal to 0, mean we're just dealing with quadrant number 1. So, this first one, let's get it in the correct form. Let's get y by itself on the left-hand side. Y less or equal -1/2 x plus 12. So the straight line associated with this, we would just replace this with an equal sign, and maybe I will continue this down below. The line would be y equals -1/2 x plus 12. Since that's a less than or equal, we're going to do solid line, and we're going to do less than means lower half plane. So let's graph this line. The y-intercept is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the slope is -1/2. So down 1 to the right 2. Down 1 to the right 2. I'm going to plot a bunch of these points, and then we'll draw the straight line through all of them. Okay, that's our first line. And remember, the half plane associated with that would be the lower half plane. The second inequality, y less than or equal to x, well, that one's pretty easy. The line associated with it is just y equals x, and again we'll do solid, and we will do lower half plane. Y equals x has 0 for the y-intercept, and a slope of 1. So now we're dealing with the lower half plane of this line and the lower half plane of this line. So far we're talking about just this region right in here. The last inequality to look at, number 3, would be the line associated with it would be y equals 4. And this is a greater than or equal. So again, we'll have solid, but in this one, we're going to do the upper half plane. So the line y equals 4 is a horizontal line. We go up 4, 1, 2, 3, 4. That horizontal line. So it should be easy which region we're going to shade, our feasibility region. It's the only single region that's below this line, below this line, and above the horizontal line. So it's going to be exactly this triangle. Okay, that wasn't too bad. Now let's circle, identify the 3 vertices, vertex points, corner points, because that is where the maximum will occur, either here, here, or here. It's always at a corner point. So let's make a small table, if we can, with the 3 points. The 3 corner points would be 1, 2, 3, 4. 1, 2, 3, 4. One of the corner points is, let me write over here, 4, 4. And then the profit for that point, 8x plus 3y, would be 8 times 4 plus 3 times 4, because this is our xy pair. X is 4, y is 4. So 8 times 4 plus 3 times 4 is 32 plus 12, or 44. The next point I'll look at is this point. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4. It's 16, comma 4. And that would give us, since x is 16, it would be 8 times 16 plus 3 times 4. 8 times 16, I believe, is 128, plus 12 would be 140. All right, for the third one, I'll put the point over here. This point is going to be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that point is 8, 8. So I'm going to plug in 8, 8, and we get 8 times 8 plus 3 times 8. This is going to be our profit, which is equal to 64 plus 24, which is 88. So the three values we look at for profit at the three corner points are 44, 140, and 88, and we find the max. And that's the winner. So to maximize this profit function, the maximum profit within this feasibility region, it always occurs at a corner point. It would occur at this point right here, which is 16, 4. X equals 16, y equals 4. And the value of the profit at that point would be 140. All right, let's do another example. We're going to maximize again this function. I was going to say a profit function, but it's just called an objective function, so it could be any type of a function that we want to maximize. So as usual, we've got these two inequalities, which mean we're dealing only with quadrant number 1. And let me write down the line associated with each of these. This would be 1, 2, 3, 4 inequalities that we're going to deal with. Y equals 12, and since the inequality portion with it is a less than or equal, we'll have solid and we'll have lower half plane because of the less than. So the line y equals 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like that. And so far we're dealing with the lower half plane. But the next one gives us a line of y equals 8. And since it's greater than or equal, well, we'll still have a solid. But greater than means we do the upper half plane. So y equals 8. If this was 12, 11, 10, 9, 8. In the upper half plane, so far we're talking about below this line and above this line, just this strip right in here. But let's keep going. Y less than or equal to 4x. The line would be y equals 4x. It'll be a solid line. And a lower half plane. Y equals 4x. It has 0 as the y-intercept and a slope of 4. So, starts here, and then we go, slope of 4 means 4 over 1. Go up 4, 2, 3, 4, over 1. Up 4 over 1. Up 4 over 1. Oops, 4 over 1, up 4 over 1. Up 4 over 1 would put me here, and then there. Okay, now, this one is all not too far away from being a vertical line. So we're going to be dealing with the lower half plane. So is it this half or is it this half? Well, the lower half plane, you could just drop a line segment anywhere from this line, and it puts you in this half plane. You'd have to go up. The upper half plane would be this one right here. Here's the lower half plane. All right, and then the last one, the line would be y equals 1/2 x plus 4. And this will be a solid line just like the rest of them. And I'm just going to write lower half plane because it's less or equal. So this one has a y-intercept of 4. 1, 2, 3, 4. Slope of 1/2. So I go up 1 to the right 2. Up 1 to the right 2. Up 1 to the right 2. And continue like this. And then I'm going to connect all these dots with a straight line. Well, let's see. That is the lower half plane. And that was the lower half plane. Let's see. I think I'm going to make one small change here. I'm going to make this an upper half plane. I'm going to change this to greater or equal. I think that's what I intended this to be. So it's going to be an upper half plane. I intended it to be this four-sided region right here, and I think that's exactly what we'll get now. So we're going below this line, the lower half plane, above this line, the upper half plane, so we're in this strip, and then we're with the lower half plane of this guy, so it means everything over here, and then we're in the upper plane of this, upper half plane of this line, which restricts us to be all in this region right here. So this four-sided region is our feasibility region, or the solution to all of these inequalities. So that means we have 1, 2, 3, 4 corner points, 4 vertex points, for which I'm going to make a table so we can figure out the z, this function's value, at each one of these 4 points, and we'll choose the one that is the largest. So let's write down our table. Vertex, and then z is equal to 10x plus 6y. All right, let's write down all the vertex points. 1, 2, comma, 1, 2, 3, 4, 5, 6, 7, 8. This point is 2, 8. Let's go over to this point. 1, 2, 3, 4, 5, 6, 7, 8. That one also has a height of 8. So this point here is 8, comma, 8. And now we'll deal with the next two. This point is 1, 2, 3, comma, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3, comma, 12. And the last remaining one is this point over here, which would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let me write that down. 16, comma. The height is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So just as a reminder, that point is 16, 12. Okay, so now let's compute the z value at each one of those 4 points. This would be let me write it as 10 times 2 plus 6 times 8. 10 times 2 plus 6 times 8 is 20 plus 48. That's 68 for the first point. 8, 8 would be 10 times 8 plus 6 times 8. That gives us 80 and 48, which is 128. So far that's the winner. It's the bigger of the two. Let's move on to 312. 10 times 3 plus 6 times 12 is 30, plus 6 times 12 is 72. That's 102. So 128 is still the winner. I think this one's going to end up being the winner, though, 16 and 12. 10 times 16 plus 6 times 12 is, let me see, that's 160 plus 6 times 12 is 72. So that would be 230. So yeah, that's by far the biggest. So we were asked to maximize the objective function, and the maximum value of that z, subject to all these constraints, is this number right here. That's the largest possible value for z taken anywhere in this feasibility region. If we were asked to minimize it, it would have been at 2, 8, where we only had a value of 68.